Oh, welcome back to our course on advanced quantum mechanics. This is lecture 18. In the previous lecture, we covered the uncertainty principle, the generic uncertainty principle, and it looked like this. Assume f hat and g hat are observables, and then assume that psi is some initial state. Prepared at time t0. And then we run the experiment. We run this experiment many times. We run the experiment with this initial state many times. Experiment many times. In principle, infinitely many times. So we say we have an ensemble. An ensemble of runs of the experiment. We don't have to run the experiments one after the other. We could also prepare the experiment many times in parallel and run it in parallel many times. Either way, we run the experiment many times, and then at experiment time, at time t, larger t0, but a fixed time t, we measure either f hat of t or g hat of t in sub-ensembles respectively. So we run the experiment 1,000,000 times, and 500,000 times we measure f hat at t, and the other 500,000 times we measure g hat of t. And then we measure them, and from that we obtain what the mean value is of f hat. At time t, we also measure the mean value of g hat of t, and of course from that we can also work out what the standard deviation was for them. And then what we proved last time is that delta f at time t, delta g at time t is larger or equal to 1/2 absolute value of the expectation value of the commutator. You see, when we calculated this, when we proved this last time, we just didn't specify the time variable. And we obtained a result that's simply true at all times. However, in this course now, we are shifting towards time dependence. We are shifting our attention now away from the foundations, the kinematics, towards what happens in dynamics. So the point I want to make here is that the general uncertainty principle between any two observables f and g holds at all times. So the uncertainty relations hold at all times t. Okay, so that's all good and fine, but there is, in addition, another type of uncertainty principle which does not fit that scheme. An uncertainty principle which is concerned with the dynamics instead. See, this is a static uncertainty principle. It relates stuff at one time to each other. the uncertainties and the means at one time. At that time is arbitrary, but the uncertainty principle itself is not concerned with the actual dynamics. Now, there exists, however, no, let me just write how, however, there exists an additional type of uncertainty relation, which just doesn't fit that sort of scheme. And in order to explain that, let me draw from daily experience here. Let's consider the grade average or the grades of a student during their career. The grades of the student fluctuate. Sometimes, you have a good day in an exam, sometimes not such a good day in an exam. So your grades fluctuate, and they fluctuate around your personal mean grade, your personal average grade. Now imagine you look at your grades and you think, I want to improve them. I want to cut out YouTube watching, for example, in the hope that that gives you more time to dedicate towards your studies and to improve your grade point average. All right, so let's say you cut out YouTube, you study more, and then sometime later, you check your average again. Let's say the next term, 2 terms later, you check your average, and you find your average has improved. Now, can you credit your strategy for that? It's not so obvious, right? Because grades are fluctuating anyway. So if you find that the average has gone up, well, maybe that was just a fluctuation. It would have happened anyway. So how do you know whether whatever measure you took to improve the grades have already improved your grades, have already had an impact themselves, and that it's not just a fluke, a statistical fluke? Now, there is a method to distinguish whether it was a fluke or whether you're already seeing a statistically significant change. And that is, of course, that you compare the amount of improvement in the grade point average to the size of your typical grade fluctuations that you normally have anyway. If the improvement in the GPA is much larger than the typical fluctuation size, then obviously your result is significant. If, on the other hand, the improvement is small compared to the size of the usual fluctuations, well, then it could be a fluke. So what we need to do is this: consider GPA dynamics. And I don't mean the cumulative GPA, but the momentary GPA. So the threshold for significance of change is this. We compare the change in GPA to the size of the fluctuations. So what is the threshold to be able to say that there has been a statistically significant improvement? Well, what we need to do is compare improvement with standard deviation. So basically what we say is that the absolute value in the change of GPA, when that is equal to the average this dot is too much, equal to the average standard deviation. I'm not just saying a standard deviation of GPA. I could have just said if the change of GPA is equal to the standard deviation of the GPA, that would be the threshold, right? So that would be a guess, but actually the threshold, I mean, to be accurate, the standard deviation of the GPA can change over time too. And so what we need to look at is the average standard deviation during the time period that we are considering. And why is that a good definition of a threshold? Well, it is because you know that if something is more than a standard deviation away from the mean, well, then you have a better than chance probability that it's significant. Remember that if you have a Gaussian distribution of some random variable, then 68%, which is more than half of all the values of that random variable are going to be within one standard deviation of the mean. So it's statistically significant in that sense if you're outside the interval of one standard deviation. So let's adopt that criterion and let's put this now into a mathematical form. And obviously we are aiming towards quantum physics for this, but let's just still write it down in terms of grades for a moment. So assume that g of t is some sort of hypothetical grade function, is a grade function. Then we say that the threshold for statistical significance, the threshold is that the absolute value of the change, and unfortunately it can also go down, so we take the absolute value of it, so the threshold is the threshold of statistical significance of a change. Uh-oh, just a moment. My laptop is running out of battery here. All right, hopefully this is now all cabled up. Right, so what I wrote down is the GPA at the later time, T naught plus delta T, minus the GPA at the earlier time. So this is the change of GPA, and we take the absolute value of that. If the absolute value matches the, so the threshold of statistical significance is reached if this is equal to the average delta G over time interval T naught to T naught plus delta T. Interesting, this is the word to, and this is T naught. All right, so this is to say the threshold is achieved, this threshold of statistical significance is achieved if the following is true: G of T naught bar is equal to, and now how do we calculate that average? Well, it's 1 over the size of the time interval times the integral from t0 to t0 plus delta t, and then it's delta g of t prime d t prime. And so we're integrating the delta g, and then we divide it by the overall time interval, and that gives us the average standard deviation. So that's the threshold here for statistical significance. If this is larger than the right-hand side, then we say, yeah, we see an improvement. It's better than chance. Now, let's move on to quantum mechanics. So, in quantum mechanics and in quantum theory in general, it's very similar. Consider an observable f hat of t. Then it fluctuates with fluctuations of size delta f of t. But also, the mean value of f of t can change over time. Then, similar to the issue with the grades, we can ask, how do we know that we observe a change in the mean value when there are fluctuations? Now, obviously, the answer has to be, if the change in the mean value is larger than the standard deviation, then we start being confident that we've seen a change, an actual change in the mean value here. So we adopt the following criterion, and that's a definition. So definition. We say we start, this is meant to be an A, start observing a statistically significant change in f bar of t over the noise delta f of t if, and now we adopt an equation that's very similar to what we had up here, this one, namely if the expectation value of f at the later time minus the expectation value of f at the earlier time in absolute value is equal to the average of the change of the average of the standard deviation of f. So integral from t0 to t0 plus delta t, and then it's delta f of t prime d t prime. So that's the criterion. If the left-hand side is smaller than the right-hand side, then we say that we haven't seen statistically significant changes yet. If, on the other hand, the mean value has changed so much that it is exceeding the average variance, the average standard deviation that we incurred in that time interval, then we say it's statistically significant. So we adopt this as a definition of the threshold between actual change and just quantum noise, quantum fluctuations. This is a very commonly adopted criterion when it comes to distinguishing a signal over the noise. In our case, the signal is a change in the mean value of an observable, and the noise is the quantum fluctuations of the observable around its mean value. So no. So this means that delta t here is the minimum amount of time to see a statistically significant change in f bar of t, starting from t naught. And let's just write out what the delta t is by taking this equation here and putting the delta t on the left and dividing by that expression, namely and now we need, let's write it like this. Yeah, well. Okay, so what we have is that delta t is equal to, and then we have in the denominator all of this. So we have f of t naught plus delta t bar minus f of t naught bar, absolute value of this. And in the numerator, we have that integral here. So we have the integral from t naught to t naught plus delta t of delta f of t prime dt prime. So this is the threshold time. If we follow the dynamics that much of time, then the threshold can be exceeded. Now let us calculate this threshold time, delta t, for a concrete system. Let us calculate delta t. Now, first of all, we have to make an assumption. Assume that the quantum system is isolated. So we leave the quantum system alone, we are not messing with it. Why do we make that assumption? Well, if we don't make that assumption, then anything goes, because you could just dramatically interfere with your system. Your system wants to do its own thing, but you hit it with a hammer. And then, of course, observables will change very quickly what their mean values are. So there's really nothing you can say if you allow yourself to mess with your system in arbitrary ways. So therefore, let us consider a quantum system that is isolated. That means, so we assume that dH by dt is equal to 0. So nothing is from the outside changing the Hamiltonian of our system. Then we have the following. We have, for all observables, f hat, we have that the Heisenberg equation of motion holds. Remember that the Heisenberg equation of motion is only valid for an isolated quantum system. We have not yet in this course investigated how quantum systems behave when they interact with another quantum system or with the outside world. We will cover that. But for now, we just derived the Heisenberg equation for an isolated system. So we have the Heisenberg equation of motion, and we also have the uncertainty principle, of course. And in particular, we have that delta F of t and then delta H of t, that's the uncertainty that our system has in its energy, is larger or equal to 1/2 absolute value. You know, I'm just writing down the ordinary uncertainty principle that we derived in the previous lecture. I'm just choosing for the two variables, for the two observables, that they are F and H, the energy. F is an arbitrary observable, H is the Hamiltonian, which is an observable like any other observable as well. So, and then here we have the commutator of F hat and H hat. All right, so we certainly have the uncertainty principle holding at all times, and there's a t, of course, and this also is a function of t. The state, of course, is independent of the time. It's the initial state vector. Well, and we have the Heisenberg equation of motion, which says that df hat by dt divided by dt, time derivative of our observables, is 1 over I h bar, and then the commutator of f hat of t and h hat. Where h hat does not depend on time because by assumption it's an isolated system that is not being interfered with. Well, then we can put these two equations together because, oh, there is no of t in here. Right. So we can put these two equations together because here we have the commutator of f and h, and here we have the commutator of f and h. So we can put that into here. Therefore, we have that, oh, let me write it here, delta f of t, delta h of t is larger equal 1/2 absolute value, the expectation value of the commutator, but this is going to be I h bar and then df hat of t by dt psi. I just used that the commutator can be expressed as the time derivative. And what is this then? Well, this is equal to h bar half, because we can pull this h bar out. The I gets obliterated by having taken the absolute value here. And then we have the absolute value of, well, we can write this as d by dt of psi, and then of f hat of t psi, like this. Why is it legal to pull the d by dt outside of the formation of the expectation value? Well, it is because psi is the initial state vector, and as such is of course not time dependent. The only time dependence in this is in the f hat. If you want to convince yourself of this, you could also insert here a resolution of the identity, there a resolution of the identity, and then you get that this is a matrix, and this is a row vector, and this is a column vector, and the row and column vectors are constant, and the matrix is dependent on time. And then you see that you can pull out the derivative because the vectors don't depend. I mean, these coefficient columns and rows do not depend on time. Okay, so we have reformulated our uncertainty principle in this form now. And we can rewrite it as h bar half, and then it is absolute value of d by dt of f bar of t, right? Because that's what this is. This is equal to this. Okay, now where are we aiming with this anyway? Well, we want to calculate this thing here, right? We want to calculate what is the critical time from which onwards the system has evolved so much that its observable f hat has changed its mean value by at least a standard deviation. What is that time? How long do we have to wait until an observable f hat has changed its mean value by at least a standard deviation? So what we need to calculate in particular is this integral over delta f of t. Now we have here an expression, delta f of t. Let's just integrate the entire thing. So what do we have then? Well, then we have integrate. So then we have the integral from t naught to t naught plus delta t of delta f of t times delta h. And actually, let me remind you that this is not time dependent because because h, the Hamiltonian, is not time dependent. So neither is its expectation value or its variance. So we integrate that over t. And then we find that this is larger equal to what we get when we time integrate the right-hand side. So integral from t naught to t naught plus delta t, h bar half, and then d by dt, f of t bar dt. Now we can pull this delta h because it's a constant number in front of the integral. So what we obtain then is that delta h integral t naught plus delta t, delta f of t dt larger equal to, you see, well, first of all, we can pull out a 1/2 h bar, but then wouldn't it be nice if we could say there's an integral here and then we are integrating over the time derivative, and then we can use the fundamental theorem of calculus because we integrate over a time derivative. So the integral of a derivative is just a function at the endpoints of the integral, right? But no, because there's the absolute value here. But remember that this is certainly larger than if we put the absolute values over here. So therefore, our inequality is certainly also obeyed if we put the absolute values symbols over here. T naught to t naught plus delta t, and then d by dt of f of t bar dt, right? It's just the usual estimate of integrals. All right. This is very helpful because this, of course, simplifies, right? It is f bar of t naught plus delta t minus f of t naught, the absolute value of it. Well, we now obtain from this, if we take this, if we divide the entire equation by that, we obtain something that almost looks like an uncertainty principle of the usual kind. We have delta H times this times the integral from T naught to T naught plus delta T. I know this is going to look ugly, but give me a sec and you will see it all becomes very beautiful. Divided by f of T naught plus delta T bar minus f of T naught bar larger equal to h bar half. Now that looks like a mighty complicated uncertainty principle, but have a close look at this thing here. And then, see, it's the integral here over delta f divided by the distance between the mean values, by the change in the mean values. Do you remember? This is simply delta t. Here we go. Delta t, the critical time from which onwards the mean value of our observable has drifted so much that the drift is larger than the standard deviation and the mean standard deviation, right? So this is exactly our delta t. That's the critical time. So what we obtain therefore is that delta h, delta t, larger equal h bar half. This is the famous time energy uncertainty principle, or uncertainty relation. And notice something curious. The observable f hat has dropped out of it. There is no f hat in our equation in red anymore. And what that means is that this uncertainty principle holds for all f hat, for all observables. So let's summarize what the conclusion here is. So the conclusion is if an isolated quantum system is in a state psi with, or is prepared, with an initial state psi with delta h larger 0, then, delta h doesn't change, because dh by dt equals 0 due to isolation. Okay. And it takes at least the amount of time, it takes at least the amount of time delta t larger equal to h bar over 2 delta H. Is this legible? Delta H. I just solved the uncertainty principle here for delta T. Right? It takes at least the amount of time delta T, or an amount of time delta T, I should say, because it's an inequality. An amount of time delta T larger equal H bar over 2 delta H for any observable f hat of the system to change its f bar of t by a mean standard deviation delta f bar, where delta f bar is equal to 1 over delta t integral t naught to t naught plus delta t delta f of t dt, right? It's just the average standard deviation in the time interval in question. So this is the famous time energy uncertainty. Time energy uncertainty principle is having some surprising consequences. Namely, if a quantum system has a known fixed energy, i.e., if the state psi is an energy eigenstate, so if we have that that is, if psi, i.e., if psi equal to some energy eigenstate with h hat acting on the energy eigenstate is producing some energy eigenvalue, well, then, and I think we covered it before, but let me just prove it to you again because it's so important. If an observable is in an eigenstate if a system is in an eigenstate of an observable, then the uncertainty in that observable is vanishing, and vice versa. So, if the system is in an energy eigenstate, then we have that the energy fluctuations delta H squared are vanishing. Let's prove this. And what I'm calculating now could be calculated also for any other observable if the state of the system was an eigenstate. But let's assume we are dealing here with an energy eigenstate. If we're dealing with an energy eigenstate, what is then the energy uncertainty? Well, it is h hat minus h bar squared psi. That's the variance. But this then is E h hat minus h bar squared. Oops, it's an E. E, which is, well, you see, the h hat acts on these energy eigenstates, producing the energy eigenvalue, which is E, right? This is E. So we obtain here that this is E minus E squared, E, which is 0. Let me just quickly show you that this is the case. So what is H bar? It is E H hat E, and obviously this is E. E is E. Right, so what we obtain is that it is 0. But what does that mean? It means that if we know for sure what the energy of a quantum system is, if we know for sure what the energy of an isolated quantum system is, then, so if delta H is equal to 0, so if we are in an eigenstate, then by the uncertainty relation, we have delta T is infinite, right? Because we have delta T larger or equal to H bar over 2 delta H. And if delta H goes to 0, delta T goes to infinity. This is weird, isn't it? Because it means that if we know the energy of a quantum system, if the system is in an energy eigenstate, then it appears that no matter how much patience you have, you will never see that the mean value of any observable changes by standard deviation. In fact, the mean value of any observable is completely frozen. The entire system is frozen. If a quantum system, an isolated quantum system, is in an energy eigenstate, then that system is completely frozen. None of its observables can change in time. Let's check this. In fact, if psi equal to E, an energy eigenstate, then all observables are frozen. Let's just calculate it. Remember, we have that d by dt of f bar, the expectation value, can be written like this. It's d by dt of, well, we have E now. So E, and then we have here f hat of t E. Remember, this is f bar of t. And the E is just an initial state, right? So this has no time dependence. So we have this. And therefore, we can write this as E and then d by dt of f hat of t E. And this can therefore be written as E. And then remember the Heisenberg equations of motion. They tell us that this is 1 over IH bar commutator of f hat of t with h hat E. Let's write it out. This is 1 over IH bar, and then it's E, and then it's f hat of t h hat minus h hat f hat of t and E. And you see what's happening now is that this h hat can act to the right on this E to produce the eigenvalue E. And this h hat, being self-adjoint, it can also act to the left in the same way, producing the eigenvalue E. So what we obtain is that this is 1 over IH bar, and then it is E, well, all right, let me just write it out. So then it is f hat of t E minus E f hat of t E, which is E being an eigenvalue over IH bar, and then we have E, E, and then f hat minus f hat, E equal to 0. So the conclusion is that if a system is in an energy eigenstate, then d by dt of f bar of t is equal to 0 for all f hat for all t larger t naught. So if a quantum system does not fluctuate in energy, if its energy is sharp, we are dealing with an energy eigenvector, then the system is completely frozen. The conclusion is that in nature, for anything to happen, for a flame to burn, for a car to drive, for a quantum computer to compute, for anything to happen, the energy must be uncertain. It must be quantum uncertain. It doesn't suffice that the energy is fixed and we don't know what it is. No. It has to be, the system has to be in a state that has quantum fluctuations in the energy. The quantum fluctuations in the energy, in this sense, are the drivers for any kind of dynamics. No dynamics without energy uncertainty. So what we notice is that the more energy uncertainty, delta H, the faster the dynamics of an isolated quantum system can be. This is relevant, for example, for quantum computers. There, the central processing unit of a quantum computer, the so-called quantum gates, need to be isolated in order not to lose their so-called coherence. We will get to that in detail later in the course. They need to be isolated systems as much as possible. Only when we want to read out what's happening, then we will interfere with them. But what this also means here is that as long as the system is isolated, it has a speed limit, which is determined by its energy uncertainty. Okay, so this is as far as we got today. See you then.